Have you ever looked up at the night sky and felt a profound sense of smallness? A feeling that what we see, the familiar moon, the steady planets, the distant glimmer of stars, is just the serene surface of a far more dynamic and chaotic universe? We live our lives on this tiny blue marble, largely unaware of the silent, epic dramas unfolding in the vast emptiness of space. But every now and then, the cosmos pulls back the curtain. It sends us a messenger, a traveler from the void, an object so strange, so extreme, that it shatters our comfortable notions of how the universe is supposed to work. Right now, at this very moment, such a visitor is hurtling through our cosmic neighborhood. It's a ghost in the machine of our solar system, an ancient wanderer that is forcing us to ask one of the most fundamental questions in astronomy. How is what we're seeing even possible? If you love exploring the deepest mysteries of the universe and want to join us on this journey to find the answer, make sure you subscribe and hit the notification bell so you don't miss a single discovery. Picture this in your mind's eye. Don't think of a star blazing with fusion or a gas giant swirling with colossal storms. Instead, imagine an atmosphere, a delicate, ethereal, and utterly gigantic bubble of gas stretching an almost unbelievable 696,000 kilometers across the vacuum of space. That isn't a typo. We're talking about a ghostly envelope so vast it could comfortably swallow our own sun with room to spare. This isn't the fiery corona of a star. It's the invisible spectral cloak surrounding what might just be the most extraordinary celestial guest our solar system has welcomed in decades. This is the story of Comet 3I-ATLAS, and its scale is, for lack of a better word, terrifying. As you listen to these words, this interstellar comet is on a precise, unalterable trajectory, racing towards its closest encounter with our Sun. It's dragging behind it this colossal atmosphere, a sea of carbon dioxide, so enormous it almost beggars belief. Our eyes on the sky, incredible observatories like Spherix, have painstakingly mapped this spectral giant, revealing what astronomers call a coma. It's a beautiful technical term for a comet's fuzzy, glowing atmosphere. But in the case of 3I-ATLAS, fuzzy feels like a wild understatement. This coma isn't a mere halo. It's a celestial entity in its own right, extending at least 348,000 kilometers in every single direction from its heart. Go ahead, do the math. You're looking at a phenomenon that is roughly half the sun's diameter and width. Let that sink in for a moment. An object visiting our solar system has unfurled an atmosphere that rivals the size of our own star. What could possibly be powerful enough to generate such a spectacle? But here's where the story takes a sharp turn, where the awe begins to mix with sheer bewilderment. This isn't some blazing inferno you could spot with a pair of backyard binoculars. The source of this half-sun-sized marvel, the comet's nucleus, its actual solid, rocky heart, remains frustratingly, impossibly small and dim. Our most powerful tool for peering into the cosmic darkness, the legendary Hubble Space Telescope, has strained its extraordinary vision to get a measure of this thing. And the best estimates it can give us? The nucleus of 3I-ATLA is no more than 5.6 kilometers across. It could, in fact, be as small as a few hundred meters. Think about that. The engine driving this stellar-scale phenomenon is smaller than Manhattan Island. A cosmic pebble, a city-sized chunk of ice and rock, is somehow generating an atmosphere 55 times wider than the entire planet Earth. This is the question that is keeping astronomers awake at night, the central paradox that makes 3I-ATLAS so compelling. The question is elegantly simple, yet profoundly difficult to answer. How? How can something so minuscule create something so impossibly large? It's a cosmic magic trick of the highest order, an illusion so grand it seems to defy the very laws of physics we hold dear. And as we stare into the heart of this mystery, a more unsettling question begins to surface. What does this impossible visitor, this ghost from another star, reveal about the terrifying, incomprehensible scales on which our universe truly operates. Are there other, even grander phenomena, drifting silently between the stars, completely invisible to us, simply because we don't know how to look? Stay with us. Join us on this journey as we unravel the enigma of 3I-ATLAS, because what we have discovered about this ancient wanderer, its origins, its bizarre chemistry, its dramatic journey, will do more than just answer a few scientific questions. It will fundamentally change how you see the cosmos and your place within it forever. This isn't just the story of a comet. It's a story about the sheer, unadulterated power of nature, a reminder that the universe is far stranger, more magnificent, and more terrifying than we can possibly imagine. To even begin to comprehend how something so small can generate a spectacle so vast, we have to peel back the layers of 3I Atlas and look at what it is actually made of. The secret, the key to this entire mystery, lies hidden in its alien chemistry. You see, we're familiar with comets. We think of them as dirty snowballs, cosmic wanderers that put on a beautiful show as they get close to the sun. For most of the comets born in our own solar system, that snow is primarily water ice. As they approach the sun, the warmth causes this water ice to sublimate, to turn directly from a solid into a gas-spewing water vapor into space to form a coma and a tail. It's a process we understand well. But 3I Atlas? Well, 3I Atlas decided to be different, radically different. This interstellar visitor isn't powered by water. Instead, it's belching a truly prodigious amount of carbon dioxide into space at a rate that would make a soda factory blush with envy. And here's the crucial piece of the puzzle. Carbon dioxide, unlike water, is an incredibly volatile substance. It doesn't need the intense heat of the inner solar system to come alive. It starts sublimating, turning directly from ice to gas at much, much colder temperatures. This single chemical quirk changes everything. It means that 3I Atlas began its spectacular atmospheric show while it was still incredibly far from the sun, deep in the cold, dark outer reaches of our solar system. It didn't wait to get close. It started building that colossal, half-sun-wide envelope long before we even knew it was there. Think of it as the solar system's most extravagant and baffling magic trick. A tiny, almost invisible performer steps onto a vast, dark stage, and with a subtle flourish, creates an illusion so massive, so overwhelming, that it completely defies our sense of scale and proportion. The coma, of course, isn't solid. You couldn't stand on it. It's more akin to a cosmic fog, an incredibly tenuous collection of individual gas molecules expanding into the perfect vacuum of space at speeds that would liquefy any atmosphere we re-familiar with on Earth. It is a ghost in every sense of the word. But its sheer, mind-boggling size creates problems and challenges that astronomers have never really had to grapple with before. Take something as simple as photography, for instance. When our observatories try to capture an image of 3I Atlas, they're not just pointing a camera at a single object. They're shooting through some of the densest, most crowded starfields in our entire galaxy. The comet's trajectory, its cosmic flight path, just so happens to carry it directly across the shimmering, star-dusted plain of the Milky Way. Every single observation session becomes an incredibly difficult exercise in stellar hide-and-seek. To track the comet's motion, telescopes have to lock onto it and move with it. As they do, the countless stars in the background streak across the image, creating pictures that look less like scientific data and more like beautiful, abstract art. It's a challenge that tests the limits of our technology and our ingenuity. And the challenges don't stop there. This incredible carbon dioxide atmosphere, the very thing that makes 3I ATLAS so special, is also largely invisible to us. It shines brightest in infrared light, a wavelength of light that our eyes cannot see. To specialized detectors, to the powerful infrared vision of telescopes like the James Webb Space Telescope, 3I ATLAS resembles a colossal, glowing soap bubble drifting silently and serenely through the starfields. Its edges are so faint, so ethereal, that they seem to just blur into the blackness of space, fading into nothingness. The part of the coma that you might actually see through a powerful optical telescope, the visible coma, is much, much smaller. It's perhaps only 26,000 kilometers across. Now, that is still massive by any earthly standard, more than twice the diameter of our planet. But it is a mere fraction of the true infrared monster lurking just beyond our sight. This profound disconnect between the visible and the invisible scale should make us all feel a little uncomfortable. It should make us pause and wonder, how many other colossal cosmic phenomena are we missing simply because we're looking in the wrong wavelengths? How many other half-sun-wide atmospheres have drifted silently past our planet, completely unnoticed, just because they don't happen to glow in the narrow band of colors our ancestors evolved to see? The universe, it seems, is broadcasting on countless channels, and for most of human history, we've only been tuned to one. But this ghostly carbon dioxide envelope does more than just create a spectacle. It tells us something profound about where 3I-ATLA came from. Most of the comets born and raised in our solar system are water-rich. Their composition is a direct reflection of the conditions in the protoplanetary disk where they formed, the swirling cloud of gas and dust that gave birth to our sun and all its planets. But a comet this fantastically rich in carbon dioxide suggests a very different origin story. It whispers of a formation in a colder, more distant environment. It speaks of a birthplace far beyond what we consider normal for comets in our own system. It even opens the door to a truly staggering possibility that 3I Atlas wasn't born in our solar system at all. It may have formed around a different star entirely. So, when we look at this comet, we're not just witnessing a large coma. We are seeing, quite literally, evidence of alien chemistry. And as 3I Atlas continues its relentless journey toward its closest encounter with the Sun in October, that already enormous atmosphere is expected to grow even larger, even more spectacular. More heat means more sublimation. More sublimation means more gas production. More gas production means more expansion. The half-sun-wide envelope we're witnessing today might, incredibly, be just the beginning. And here's where the story takes on a truly unsettling, almost ominous tone. The sheer size of this coma isn't just a curiosity. It has profound physical consequences. It determines how the comet interacts with the solar wind, that constant, powerful stream of charged particles flowing out from our star. A bigger atmosphere means a bigger target. A bigger target means more dramatic, more violent interactions. It creates more opportunities for the kind of spectacular space weather phenomena that can literally rip a comet's tail apart or create breathtaking light shows millions of kilometers long. The stage is set for a celestial performance measured not in theaters or stadiums, but in astronomical units. 3I Atlas isn't just visiting our solar system. It's actively transforming a region of space larger than our sun into its own personal laboratory. And we, all of us, are invited to watch what happens when half a sun's worth of atmosphere meets the full, untamed fury of a star at the peak of its power, at solar maximum. What secrets will be revealed in that cosmic collision? What will this impossible visitor from another time and place teach us about the true, terrifying scale of the universe? The curtain is just beginning to rise. There's an old saying, speed kills. In the context of our daily lives, it's a warning. But in the vast, gravitational dance of the cosmos, speed reveals. The sheer velocity of an object tells you its story, its origins, its ultimate destiny. And in the case of 3I-ATLAS, its speed reveals a truth that is both exhilarating and a little bit heartbreaking. This is no lazy cosmic commuter, lazily orbiting our sun on a predictable, repeating schedule like Halley's Comet or so many others we know. No, 3I-ATLAS is moving with an almost violent purpose. At its closest approach to the Sun, it will be traveling at a blistering 68 kilometers per second. Just try to wrap your head around that. That is fast enough to cross the entire continental United States, from New York to Los Angeles, in less than 2 minutes. It is, by any solar system standard, hyperfast. And this incredible speed isn't just a jaw-dropping statistic. It is the key to understanding the single most important fact about this visitor-S journey. It will never, ever return. The mathematics of orbital mechanics are as beautiful as they are unforgiving. 31ATLAS is following a path that astronomers call a hyperbolic orbit. Unlike the closed ellipses of planets and familiar comets, a hyperbola is an open-ended trajectory. It's a one-way ticket. A comet has more than enough energy to defy the Sun's immense gravitational pull. It is, in the precise language of physics, gravitationally unbound from our solar system. This means that once it swings around our star this coming October, the Sun's gravity will act like a slingshot, accelerating it back into the interstellar void at a departure velocity of 58 kilometers per second. It will vanish back into the darkness from which it came, never to be seen by human eyes again. In cosmic terms, what we're witnessing is a fleeting, one-night stand between our solar system and a wanderer from an unknown, faraway place. This, of course, raises the most tantalizing question of all. If it's not from around here, then where exactly is elsewhere? Where did this incredible journey begin? Imagine being a celestial detective. When astronomers trace the trajectory of 3I Atlas backward through space and time, rewinding its path star by star, year by year, they arrive at a startling conclusion. This comet originated from the direction of the constellation Sagittarius, a patch of sky that, from our vantage point, lies near the blazing, star-dusted center of our Milky Way galaxy. And its journey has been long, unimaginably long. It has been cruising through the cold, silent emptiness of interstellar space for, potentially, billions of years, carrying with it the preserved, frozen, chemical fingerprints of whatever stellar neighborhood gave it birth. The age estimates are so vast, they almost lose their meaning. Multiple, independent kinematic analysis complex studies of the comet's motion and trajectory all point to the same incredible conclusion. 3I-ATLAS belongs to what astronomers call the thick disk population of our galaxy. What does that mean? Think of our galaxy as a bustling city. There are the new, bright, flashy neighborhoods in the thin, flat disk where our sun resides. And then there are the old, established, historic districts, the thick disk. This is the galaxy's old guard, ancient stars and debris with orbital characteristics that practically scream, "I was here first." The stars in this population are the galaxy's venerable elders. And so, it seems, is our comet. Some studies bracket its age at somewhere between 3 and 11 billion years. Others, pushing the analysis even further, suggest its age is likely beyond 7.6 billion years. Let that number settle in your mind for a moment. Our entire solar system, the Sun, the Earth, every planet, every asteroid, is only about 4.6 billion years old. This means that the rocky city-sized nucleus of 3I Atlas, the tiny engine driving this colossal atmospheric display, may have already existed as a fully formed object when our sun was nothing more than a diffuse, swirling cloud of gas and dust. It watched our galaxy evolve through cosmic epochs we can barely comprehend. It silently bore witness as generations of stars were born and died. It survived stellar explosions, gravitational tugs of war between giant stars, and the slow, relentless churn of galactic dynamics that eventually, somehow, ejected it from the system that gave it birth and sent it on its lonely odyssey. Just imagine what this small rock has seen. It is a time capsule wrapped in exotic ice and ancient rock, preserving the chemical conditions from an era when the universe was younger, when the recipe for making stars and planets was different. The thick disk population represents our galaxy's turbulent middle age, a time when star formation was more violent, more chaotic, and less organized than the relatively gentle cosmic suburb where our own sun and its planetary family grew up. This ancient heritage is almost certainly the reason why 3I Atlas behaves so differently from the comets we know. It's bizarre. Carbon dioxide-dominated chemistry is a direct reflection of formation conditions we simply do and see in our local neighborhood. The composition of its ices, the ratio of its dust to its gas, even the way it reacts to the heat of our sun, all of these characteristics bear the unmistakable signature of a different time and a different place. The journey itself beggars comprehension. For millions, or perhaps billions of years, 3I Atlas drifted through the profound cold between the stars. Its surface was perhaps occasionally stirred by the sting of a cosmic ray or the whisper-faint pressure of distant starlight. It would have passed through the outer fringes of other unknown stellar systems, a silent ghost in their night sky. It witnessed the birth and death of countless stars we will never know, and it slowly, patiently tumbled through the galaxy's majestic spiral arms like a message in a bottle, thrown into an infinite ocean of vacuum. So, what finally brought it to us? What cosmic coincidence delivered this messenger to our doorstep? The answer is probably nothing more dramatic than pure, unadulterated chance. It was the same gravitational lottery that occasionally sends asteroids on Earth-crossing orbits, or flings entire planets into the lonely darkness of interstellar space. Our solar system, plowing through the galaxy at a staggering 230 kilometers per second as it orbits the galactic center, simply happened to intersect the trajectory of 3I Atlas at precisely the right moment in cosmic history. The timeline of this chance encounter reads like a precisely choreographed cosmic dance. A perihelion, its closest approach to the Sun on October 29th, at a safe distance. A near miss of Earth in December, close enough for breathtaking observations, but far enough to pose absolutely zero threat. And most intriguingly, a series of close encounters with other planets, providing multiple, unique opportunities to study how an ancient interstellar wanderer behaves under the conditions of a modern solar system. But here is the thought that should give us all a moment of profound pause. 31A represents just one single data point, one lonely traveler, in what must be an enormous, unseen population of interstellar objects crisscrossing our galaxy right now. Current models suggest that millions, perhaps billions of these cosmic refugees are drifting silently through space, completely invisible and undetected until they happen to wander close enough to a star system like ours to warm up and announce their presence. So when we look at 3I Atlas, we are not just observing a comet. We are catching a fleeting glimpse of the debris field of galactic evolution itself. We are seeing the scattered, frozen remains of countless star systems that have lived, died, and ejected their children into the great cosmic void. 31A is simultaneously a visitor and a messenger. It is carrying news from stellar neighborhoods, so distant and so ancient that their very existence challenges our provincial, sun-centric view of cosmic chemistry. The terrifying scale isn't just about size. It's about time, and it's about distance, and it's about the sheer, mind-bending improbability of this very moment. An object, older than our world, moving faster than anything in our experience, has chosen this brief, fleeting moment in all of cosmic history to grace us with its presence. And when it leaves us behind in 2026, when it recedes back into the darkness, it will carry with it our measurements, our curiosity and our sense of wonder, taking a small piece of us with it into the endless dark between the stars. Forget everything you think you know about empty space. We have this ingrained image of the void between planets as a perfect, silent, tranquil vacuum. But the region of space immediately surrounding 3I Atlas is anything but empty. It's a bustling, chaotic factory of plasma physics. It's a stage for a grand play of electric fields and magnetic drama, unfolding on a scale that makes a terrestrial lightning storm look like a tiny spark of static electricity. That half-sun-wide atmosphere we've been marveling at? It isn't just a passive cloud of gas expanding peacefully into the void. It's what physicists call a dusty plasma, a complex seething soup of electrically charged particles, tiny grains of ancient dust, and invisible lines of magnetic force, all interacting in ways that would make any laboratory on Earth green with envy. It is, in every sense of the word, a living, electrified atmosphere. So how does this happen? How does a simple ball of ice and rock create such a dynamic, energetic environment? The magic begins the very moment that sunlight and the relentless solar wind hit the comet's coma. These two forces from our star act like a cosmic transformer, instantly beginning to convert the neutral gas molecules into ions. It's a process of violent creation. Picture this. As those countless carbon dioxide molecules sublimate from the comet's tiny nucleus, they are immediately bombarded by the sun's harsh ultraviolet radiation. This energetic light is powerful enough to knock electrons loose from the molecules, stripping them away and leaving the molecules with a positive electric charge. These newly created ions, these charged particles, don't just drift aimlessly into space. The moment they are born, they are caught in the grip of a powerful, unseen force, the solar wind's magnetic field. Think of the solar wind not just as a stream of particles, but as a magnetized river flowing constantly outward from the sun. These new cometary ions are instantly coupled to this flow, swept up and accelerated along invisible magnetic field lines that stretch all the way back to the sun itself. And this is how a comet's tail is truly born. It's not like rocket exhaust pushed out from behind. It's not formed by atmospheric friction. It is a delicate, beautiful structure sculpted by the gentle yet inexorable pressure of magnetized plasma flowing from our star. The ion tail of 3IATLAS will act as a cosmic weather vane, always pointing directly away from the sun, regardless of which direction the comet itself is traveling. It's a visual testament to the invisible magnetic forces that permeate our entire solar system. But here, as with everything else about this visitor, is where 3IATLAS gets particularly interesting. Its trajectory, its specific path through our solar system, seems almost tailor-made to maximize this drama. Remember its retrograde orbit? It's traveling almost directly opposite to the flow of planetary traffic. More importantly, this path will take the comet on a long, dangerous cruise across something called the heliospheric current sheet. It sounds complex, but just imagine a vast, wavy, invisible boundary that permeates the entire solar system. It is the surface where the polarity of the sun as magnetic field reverses flipping from north to south. Think of it as the galaxy's largest windsock, a colossal surface that flutters and ripples as the sun rotates on its axis every 27 days. When a comet crosses this boundary, its entire plasma environment can be thrown into chaos. Magnetic field reversals can literally tie its tail in knots, create spectacular disconnection events, where the tail appears to be violently torn away, or generate entirely new structures in the coma, as different magnetic domains clash and interact. We've had a glimpse of these phenomena before. The European Space Agency's incredible Rosetta mission gave us our first truly intimate, close-up look at the plasma environment around a comet, 67P Churyumov-Gerasimenko. And even that relatively quiet, sleepy comet developed a surprisingly dynamic ionosphere, complete with electric fields accelerating particles and plasma waves, propagating through its coma like ripples on an electrified pond. Now, just imagine what we might see with 3IATLAS. With its absolutely massive atmosphere and its incredibly high activity levels, it should provide a natural laboratory for studying these effects on a much, much grander scale. It's like comparing a candle flame to a forest fire. And the timing? It simply could not be more perfect for a spectacle. We are approaching solar maximum, the peak of the sun's 11-year activity cycle, when our star's magnetic field is at its most chaotic and violent. During these periods, events called coronal mass ejections, or CMEs, become much more frequent and much more violent. These are billion-ton blobs of magnetized plasma, hurled from the sun's surface at incredible speeds. When a CME slams into a comet's atmosphere, the results can be nothing short of spectacular. We can see the coma get compressed, the tails completely restructured, and sometimes a complete tail disconnection as the CME's magnetic field lines snap and reconnect with the comets, releasing an enormous amount of stored energy in a cosmic explosion. The physics gets even more complex, even more intricate, when you remember the dust. 3.1. Atlas isn't just shedding gas. It's also releasing countless microscopic particles of dust and ice. And in the charged environment of the solar wind, these tiny grains don't remain neutral. They become electrically charged themselves. And charged dust behaves very, very differently from neutral material. It can be accelerated by electric fields, trapped in magnetic bottles, or organized into complex, filamentary structures by plasma instabilities. Recent observations from the JWST have detected submicron water ice crystals within the coma, along with what is likely rocky debris from the nucleus itself. Each individual grain becomes its own tiny spacecraft, carrying an electric charge and responding to the complex, ever-changing electromagnetic environment surrounding the comet. The result isn't a simple cloud. It's a three-dimensional living sculpture of charged particles, constantly shifting and evolving as the comet moves through different regions of the solar wind. Now, we need to be very careful about cause and effect here. Let's be absolutely clear. Comets do not trigger solar flares or CMEs. They are simply the unlucky, or for science, the incredibly lucky victims when these solar tantrums occur. But in their victimhood, they serve as exquisitely sensitive probes of space weather conditions. The way the tail of 3I Atlas kinks, disconnects, or brightens tells us more about the intricate structure of the solar wind than any single spacecraft could ever measure directly. The crossings of that heliospheric current sheet are particularly important moments to watch. They often coincide with high-speed solar wind streams, regions where the solar wind's velocity can suddenly jump from a gentle 400 kilometers per second to a ferocious 800 kilometers per second. These stream interaction regions create compression waves that propagate outward from the sun, and when they hit a comet's atmosphere, they can create the most remarkable displays of plasma physics in action. And this electromagnetic drama isn't just of academic interest. There's a chance for a truly historic observation. Mars orbiters might just catch a glimpse of 3I Atlas during its close flyby on October 3rd. This could provide our first ever direct measurements of how the red planet's thin atmosphere and weak magnetic field respond to the presence of a comet's vast charged particle environment. Could a large cometary atmosphere actually influence a planetary magnetosphere, even at distances we previously thought to be safely remote? It's a question we've never been able to answer before. What we are witnessing around 3I Atlas is, in essence, a natural particle accelerator operating on an astronomical scale. Invisible magnetic field lines stretch and snap like cosmic rubber bands, releasing stored energy that accelerates ions to incredible velocities. Electric fields build up and discharge across distances measured in Earth diameters. And all of this electromagnetic fury, all of this high-energy drama, is centered around a nucleus that is smaller than most asteroids. The living, breathing plasma atmosphere of 3I Atlas represents one of nature's most exotic states of matter, played out against the infinite, silent backdrop of interplanetary space. It is a stark and beautiful reminder that the universe is far more electrically active, far more dynamic, than our quiet earthbound experience would ever suggest. It is a lesson that even the emptiest regions of space can become grand theaters for physics, so dramatic, so powerful, that it challenges our very understanding of what's possible. All right, let's address the elephant in the solar system. Let us talk about the idea that pops into the public imagination every single time an unusual object from interstellar space pays it a visit. Is it a probe? Is it a surveillance mission? Are we finally seeing a techno-signature, the calling card of an advanced extraterrestrial civilization? It's a captivating thought, the stuff of science fiction dreams. And so, before we dive even deeper into the genuine, scientifically backed mysteries of 3IATLAS, it's crucial that we take a moment to establish, with clarity and confidence, what we are actually dealing with here. Is this an alien artifact, or is it a natural wonder? Let's start with the basics. 31ATLAS is the third confirmed interstellar object ever detected by humanity. It's following in the cosmic footsteps of two previous, and very different, visitors. First, there was the enigmatic cigar-shaped Oumuamua, an object that sparked endless, and often wild, debates about its strange acceleration and unconventional shape. Then came 2I Borisov, a much more conventional-looking interstellar comet that, for the most part, behaved as we expected. 31ATLAS is the third chapter in this unfolding story. But here's the key difference. Unlike Oumuamua, which left so many questions unanswered, 31 Atlas is displaying every single characteristic we would expect from a natural, albeit extremely unusual, comet. It has a visible coma. We can clearly measure its gas and dust production. And its behavior, its brightening and outgassing as it gets closer to the sun, follows the predictions of physics almost perfectly. Every observation points to the same conclusion. This is a dirty snowball from another star system, behaving exactly as a dirty snowball should. Now let's tackle the safety question first, because an exotic origin can sometimes be conflated with danger. Let me put your mind at ease. 31 Atlas will never, at any point, come closer than 1.8 astronomical units to Earth. To put that in perspective, 1 astronomical unit is the distance from the Earth to the Sun. So, at its nearest, the comet will still be about 168 million kilometers away from us. That places it firmly, unequivocally, in the fascinating but completely harmless category. Mars gets a much closer shave, a flyby at 0.19 astronomical units on October 3rd. But even that represents a comfortable buffer of about 19 million kilometers. So, what makes 3IATLA so special isn't any threat it poses. What makes it a once-in-a-generation scientific opportunity is its unique combination of chemistry, scale, and timing. Its carbon dioxide-dominated atmosphere represents an extreme end member of comet composition, something we have simply never witnessed before in our own solar system. Its absolutely enormous coma is challenging our most fundamental models of how a small nucleus can generate such massive gas production. And its arrival during the peak of solar maximum provides a priceless opportunity to study the intricate dance of interstellar plasma physics under the most active, most violent conditions our sun can possibly provide. The signatures of a natural comet are unmistakable and have been confirmed by a global network of observatories. Hubble sees the classic fuzzy coma structure. The James Webb Space Telescope detects the precise spectroscopic fingerprints of sublimating ices. The Spherix Observatory maps that extended carbon dioxide envelope in stunning detail. And ground-based telescopes all over the world are tracking its predictable brightening as the sun's heating effect increases. There is no ambiguity here. But let's acknowledge the elephant's very weird cousin. The chemistry of 3IATLA is as genuinely, profoundly weird. That 8-to-1 ratio of carbon dioxide to water isn't just unusual. It's a staggering statistical anomaly. It sits 6.1 standard deviations, or sigma, above the typical composition of comets we're familiar with. In the world of statistics, anything beyond 3 sigma is considered highly unusual. A 6 Sigma event is the kind of thing that is supposed to happen only once in a billion observations. So, what does this mean? Are we just incredibly lucky to have witnessed an astronomical lottery ticket? A 1 in a billion statistical fluke? Or does the chemistry of 3I Atlas tell us that its formation environment was so radically different from anything we see in our local stellar neighborhood that it operates under a completely different set of rules? The scientific method demands that we explore the most exotic hypotheses only after we have completely exhausted all the conventional explanations. And in this case, there are actually plenty of plausible natural ways to create a comet that is this rich in carbon dioxide. Imagine, for instance, that 3I Atlas formed much farther out in its birth system than our comets did, beyond what is called the carbon dioxide frost line. This is a region so cold that CO2 can freeze directly from a gas into a solid ice. Or perhaps its youth was more violent. Maybe it was subjected to heavy radiation from a nearby massive star, a process that could have preferentially stripped away the more fragile water vapor while leaving the carbon dioxide trapped beneath. Or maybe the answer lies in its billion-year journey. Perhaps over that immense timescale, an insulating crust formed on its surface, a crust that preferentially releases the more volatile carbon dioxide while keeping the water vapor locked deep inside. Each one of these natural explanations carries its own profound implications for our understanding of how planets form around other stars. If 3I Atlas is formed in the cold, outer regions of its birth system, it tells us something important about the structure and chemistry of alien protoplanetary disks. If it was blasted by heavy stellar radiation, it helps us constrain the types of stars and stellar nurseries that could produce such an object. And if a crust evolved over its long journey, it reveals how billion-year voyages through the harsh environment of interstellar space might physically alter the surfaces of comets. The mystery is not, is it alien technology? The real mystery is, which of these amazing natural processes created this beautiful weirdo? Part of the challenge, and the frustration, is that the nucleus itself remains infuriatingly elusive. Hubble, as upper limit of 5.6 kilometers in diameter, could be hiding a nucleus as small as just a few hundred meters across. That uncertainty spans 2 orders of magnitude in mass, making it impossible to calculate precise gas production rates or to predict its future behavior with absolute confidence. We are, in essence, studying this comet by its shadow. We are forced to infer the properties of an invisible core from the magnificent atmosphere it creates. There were some early size estimates that suggested a much larger nucleus, perhaps as big as 46 kilometers across. These were based on measurements of its brightness in near-infrared light. But those calculations depend very heavily on assumptions about how reflective its surface is, about the ratio of dust to gas that may simply not apply to a visitor from another star system. The Hubble imaging constraint remains our most reliable measurement because it doesn't depend on these assumptions. It's a direct, though challenging, observation. The intense public interest in interstellar objects like this creates a very tricky environment for scientific communication. Every new observation gets scrutinized for any sign of artificiality. Every unusual measurement can spawn a tidal wave of speculation about extraterrestrial technology. In response, the scientific community has learned to present its findings with extra caution, to be meticulously clear about separating established facts from preliminary interpretations or hypotheses. This caution serves everyone well. Extraordinary claims, like the suggestion of an alien technosignature, require truly extraordinary evidence. And for 3I Atlas, that evidence simply does not exist. The comet's behavior, as extreme as it is, falls comfortably within the vast and wonderful range of natural phenomena. But let's be crystal clear. Natural does not mean boring. In fact, it might be the opposite. 31 Atlas is offering us a direct, physical sample of interstellar chemistry. It's a billion-year-old time capsule from the galaxy's ancient thick disk population. It is carrying information about the conditions of star formation that predate the existence of our own solar system. It is demonstrating plasma physics on a scale we could never hope to reproduce in any laboratory on Earth. It is providing our first-ever opportunity to study how ancient alien ices respond to the heat of our modern sun. The real mystery of 3I Atlas isn't whether it's artificial. The real mystery is how nature, on its own, managed to create something so extreme, so beautiful, and so wonderfully weird that it challenges our very understanding of what's possible. Sometimes the most profound discoveries come not from finding something we never expected, but from finding a familiar phenomenon like a comet pushed to such an incredible extreme that it forces us to tear up our old textbooks and revise our most basic assumptions about how the universe truly works. 3I Atlas is a natural comet, but it's a natural comet operating at the very bleeding edge of what nature apparently allows. And that, in the end, might be even more interesting, more inspiring than any artifact could ever be. Every great story of discovery has a beginning, a single moment where the unknown first peeks through the curtain of the known. For 3I Atlas, that moment arrived on July 1st, 2025, deep in the arid crystal-clear skies of Chile. A robotic sentinel named the Atlas Survey Telescope was doing what it does every single night, methodically scanning the heavens, searching for any faint points of light that move against the fixed background of the stars. On this particular night, its sensitive digital eyes captured something unusual in the constellation Sagittarius, a faint, insignificant smudge against the impossibly crowded backdrop of our galaxy's central regions. At that moment, it wasn't a legend. It was just a string of cosmic alphabet soup in a computer database, a 1PL3Z. Nothing in that anonymous designation even hinted at the extraordinary nature of what the telescope had just found. It was just another blip, one of thousands detected every week. But then, everything changed. Just 24 hours later, the nerve center of planetary discovery, the Minor Planet Center, issued a circular. It was an electronic bulletin known as MPEC 2025N12, sent to astronomers all around the world. And suddenly, that anonymous smudge had a name and a destiny. The object, initially designated C2025N1, was almost immediately flagged for its unusual trajectory. The initial calculations were tentative, but they were electrifying. This object didn't seem to be moving like a normal member of our solar system. The race was on. Astronomers globally scrambled to get more observations, to train their telescopes on this faint newcomer and confirm its path. With each new data point, the picture became clearer and the conclusion more inescapable. This was it. This was the one they had been waiting for. The object was officially designated 3I Atlas, the third confirmed interstellar object in human history. Now, that I in its name isn't awarded lightly. It is a prestigious, almost sacred, designation in astronomy. It means that the world's foremost orbital dynamicists, the mathematicians, at NASA's Jet Propulsion Laboratory and elsewhere, have calculated its trajectory with excruciating precision and have concluded beyond any reasonable doubt that this object's origin lies firmly outside the gravitational grasp of our sun. The mathematics behind this conclusion are both brutal and beautiful in their certainty. The comet's orbital eccentricity, a measure of how much its orbit deviates from a perfect circle, was calculated to be 1.047. Anything greater than 1.0 means the path is not a closed loop. It is a perfect, open-ended hyperbola. Its velocity at infinity, its cruising speed far from any star's gravity, was a staggering 58 kilometers per second, far too fast for it to have ever been captured by our sun. These numbers don't lie. They don't leave any room for interpretation or debate. 3I Atlas is a visitor, not a resident. But July's incredible discovery was just the end of the beginning. The moment the interstellar nature was confirmed, a new kind of detective work began. Astronomers immediately started scanning through vast digital archives of older images, a process called precovery. They were searching for earlier sightings of the comet, moments when other telescopes might have accidentally captured it in an image before its official discovery, without realizing what they were seeing. These recoveries are like finding forensic evidence at a cosmic crime scene. Each additional observation point allows scientists to extend the observational arc, to trace the comet's path through space with ever-increasing precision. Every new point tightens the mathematical constraints, refining our understanding of exactly where 3I Atlas came from and exactly where it is going. The announcement of a new interstellar object rippled through astronomical networks with remarkable speed. It was a jolt of pure adrenaline for the entire community. NASA's Planetary Defense Coordination Office, the agency responsible for tracking near-Earth objects, issued a public statement. They confirmed the interstellar nature of the comet, but also, crucially, emphasized its safe flyby distance. At the time of its discovery, 3I Atlas was a distant 670 million kilometers from Earth. It posed zero threat to our planet, but it offered an unprecedented scientific opportunity. The messaging was critical. In the age of the Internet, the words interstellar object can trigger both immense fascination and a fair amount of fear. So, almost immediately, educational outreach kicked into high gear. Astronomy websites, science communicators, and educators rushed to explain the crucial difference between an object being interstellar and it being dangerous, helping the public understand that an exotic origin does not equal an existential threat. The first images that started coming in from ground-based telescopes revealed the immense challenges that lay ahead. 31 Atlas appeared as a faint, fuzzy star, almost lost against the dense, glittering tapestry of the Milky Way's central regions. Remember, its path was taking it through the most star-crowded portion of our sky. Tracking the comet's motion required long exposures, and as the telescopes followed the comet, the surrounding stars streaked across the images, creating that beautiful but scientifically problematic abstract artifact. Despite the challenges, networks of both professional and amateur astronomers, like the Virtual Telescope Project, began their own dedicated observation campaigns, contributing to the global, collaborative effort to characterize this extraordinary visitor. Soon, the heavy hitters of the astronomical world entered the game. The Hubble Space Telescope, with its legendary sharp vision, was pointed at the comet. Floating high above the blurring effects of Earth's atmosphere, Hubble was able to cut through the comet's glare and place the first meaningful constraints on the size of the nucleus. The result was that now famous number, no larger than 5.6 kilometers across. This single observation was a game-changer. It officially established 3I Atlas as a relatively small, but as we already knew, extraordinarily active comet. The ratio of its immense coma size to its tiny nucleus diameter was already exceeding anything ever seen in our solar system's native comet population. Meanwhile, behind the scenes, teams at the Space Telescope Science Institute began preparing an observation campaign for the most powerful space telescope ever built. The JWST, this incredible observatory, would bring its unprecedented spectroscopic capabilities to bear on 3I Atlas, promising a detailed chemical analysis of its coma. These future observations would provide our first ever direct measurements of the chemistry of interstellar ices, revealing whether alien comets are built following the same rules and recipes as our local population. The discovery timeline of 3I Atlas perfectly illustrates how modern astronomy operates as a seamless global network. A survey telescope in Chile makes the initial detection. The Minor Planet Center processes the data and distributes the alert worldwide. Major observatories in space and on the ground pivot their plans to conduct follow-up campaigns. And amateur astronomers, citizen scientists from all walks of life, contribute additional crucial observations. Within a matter of weeks, 31ATLAS transformed from an anonymous sky survey detection into one of the most closely watched, most intensely scrutinized objects in the entire solar system. This entire confirmation process follows strict, internationally agreed upon protocols that have been developed over decades of asteroid and comet discoveries. The Minor Planet Center acts as the central clearinghouse, collecting observations from multiple sites, calculating preliminary orbits, and only issuing circulars when the trajectory is certain. For an object of this importance, the level of scrutiny is even higher, ensuring that measurement errors or systematic biases don't lead to a false claim of an extrasolar origin. 31ATLAS passed every single test. Its hyperbolic orbit appeared in calculation after calculation, refined and confirmed by observations from dozens of telescopes worldwide. Its velocity measurements aligned perfectly with theoretical predictions for the interstellar object population, and its trajectory traced back to a plausible region of our galaxy's ancient thick disk, consistent with kinematic models of stellar populations. By the end of July, the case was closed. The verdict was in. 31ATLAS had officially transformed from a faint smudge in the stars to a confirmed interstellar visitor, a messenger from a time and place beyond our wildest imaginings. But this incredible discovery, this entire whirlwind process of detection and confirmation, was really just the first step. It was the prologue to a much grander story. The 18-month observation campaign, spanning from now through the comet's final departure in late 2026, was just beginning. We had identified our target. We had confirmed its extraordinary nature. Now the real science, the real adventure, was about to begin. Imagine being able to read a message that has been traveling towards you for billions of years. A message not written in words, but in light. A message encoded in the subtle vibrations of molecules, preserved in a deep freeze since before the Earth itself was formed. When the James Webb Space Telescope, humanity's most powerful eye on the universe, turned its near-infrared spectrograph towards 3I Atlas, that is precisely what it did. It read the chemical message of the comet, and what it revealed was so stunning, so far outside the realm of normal, that it should make every single planetary scientist on Earth pause and reconsider what they thought they knew about how comets, and perhaps even planets, are made. The numbers that came back were stark, they were unprecedented, and frankly, they were a little bit unsettling. Let's go back to that key ratio, the amount of carbon dioxide compared to the amount of water. The JWST observations didn't just give us a single number. They painted a beautifully detailed picture of this alien ice composition. By breaking the comet's faint light down into its constituent wavelengths, like a prism, the telescope could identify the unique chemical fingerprints of different molecules. At a wavelength of 4.3 micrometers, the signature of carbon dioxide was overwhelmingly dominant, a massive spike in the data. At 4.7 micrometers, a smaller, but still significant signal of carbon monoxide appeared. And what about water vapor? It showed up, as expected, at 2.7 micrometers, but as a distinctly minor component, a mere whisper in the chemical symphony. And scattered throughout this spectrum, the telescope found the subtle signatures of fine water ice grains, each less than a single micrometer across, suspended like a delicate frost within a coma utterly dominated by carbon-bearing volatiles. This wasn't a dirty snowball. This was something else entirely. Maybe a dirty, dry ice ball. And this wasn't just a single telescope's result. In a beautiful example of scientific synergy, the Spherix Observatory independently confirmed this chemical weirdness. While JWST was doing a deep, focused dive on the chemistry, Spherix was mapping the big picture, tracing that enormous carbon dioxide envelope across its full 696,000-kilometer diameter. The fact that two completely different observatories, using completely different methods, arrived at the same shocking conclusion, eliminates any possibility of an instrumental error or a calibration problem. The verdict is in. 3I-ATLAs really is that astonishingly, unapologetically, carbon dioxide rich. But why? That is the billion-dollar question. Answering it is like trying to reconstruct the history of an ancient culture based on a single, beautifully preserved, but utterly alien artifact. The leading hypotheses read like a menu of exotic formation scenarios, each with its own profound implications. As we touched on before, perhaps 3I Atlas was born in the frigid outer suburbs of its birth system, a region far beyond the carbon dioxide frost line, where temperatures plunge low enough for CO2 to condense directly from a gas into a solid ice. This is a tantalizing possibility, but it would require the protoplanetary disk in that alien system to be much more massive and extended than the one that formed our own solar system. Alternatively, maybe the comet's youth was far more traumatic than we can imagine. Perhaps it formed in a stellar nursery alongside massive luminous stars. The intense stellar irradiation in such an environment, a flood of high-energy light thousands of times more powerful than anything our own sun could produce, might have preferentially boiled away the more fragile water ice while leaving the more resilient carbon dioxide and carbon monoxide trapped in protective ice matrices. It is a violent but plausible scenario that paints a picture of a very different kind of planetary birthplace. And then there's the third possibility, which is more subtle but equally significant: the transformative power of its immense journey. Think about what a billion years adrift in interstellar space would do to an object. The constant bombardment by high-energy cosmic rays, the relentless peppering by micrometeorites, and the gentle but persistent pressure of interstellar radiation could have created a hardened, insulating crust on the comet's surface. A crust that, like a cork in a bottle, preferentially releases the more volatile carbon dioxide that can escape through cracks and fissures, while trapping the less volatile water vapor deep beneath the surface. Each of these explanations opens a new window into our understanding of planet formation across the galaxy. If 3I Atlas formed in the cold outer regions of an alien disk, it helps us constrain the mass distribution and temperature structure of planetary systems around different types of stars. If stellar irradiation is the answer, it tells us about the violent, chaotic environments where some planetary systems take shape. And if it's all about the evolution of its crust during its long, lonely transit, it reveals how these billion-year journeys through the void might physically and chemically alter the surfaces of small bodies, transforming them in ways we are only just beginning to imagine. The sheer scale of the chemistry is staggering. The production rates derived from the JWST spectroscopy are difficult to scale down to human comprehension. Conservative estimates suggest that 3I-ATLAs is currently losing several tons of material every single second, with carbon dioxide accounting for the vast majority of that mass loss. Picture a freight train's worth of ice sublimating into the vacuum of space every single minute, expanding that already colossal coma at velocities approaching 1 kilometer per second. And what makes this even more unusual, even more of a puzzle, is that this extreme level of gas production is happening while the comet is still at 3 astronomical units from the Sun. It's still farther away from the Sun than Mars is. Most of our familiar periodic comets don't even begin to wake up to show any serious outgassing until they get much closer, typically inside of 2 astronomical units. 3I-ATLAS, on the other hand, is already operating at peak efficiency while still in the cold outer regions of the solar system, and the JWST found even more. Its sensitive spectrographs also detected the signature of a molecule called carbonyl sulfide, OCS. This might seem like a minor detail, but to a chemist, it's a crucial clue. This molecule requires very specific formation conditions, and it tells us a great deal about the sulfur chemistry in the comet's birth environment. Its presence suggests a complex interplay of carbon, sulfur, and oxygen chemistry during the comet's formation, possibly indicating that sulfur-rich ices were condensing in a protoplanetary disk with a very different mix of elemental abundances than our own solar system had. The chemical fingerprint of 3I-ATLA reads like a message from an alien world, a message encoded in the language of molecular vibrations and preserved in a deep freeze for billions of years. Each spectral line, each tiny dip and peak in the data carries information about the temperatures, the pressures, and the elemental abundances in a stellar system, so distant that its very existence was completely unknown, until this small icy messenger arrived to tell us about it. We are not just studying a comet. We are conducting archaeology on a galactic scale, using the tools of chemistry to reconstruct the conditions that prevailed when our galaxy was younger, when star formation followed different rules, and when the ingredients for planets were being mixed in a completely different cosmic kitchen. Every grand machine has an engine, a central core from which all its power originates. For a comet, that engine is its nucleus, the solid, dirty snowball at its heart. But the nucleus of 3I-ATLA presents us with one of the most maddening and compelling mysteries in modern astronomy. We are faced with an object that is simultaneously too small to see clearly, yet far too active and powerful to ignore. It is the ghost in its own spectacular machine. We see the magnificent results of its work, the half-sun-sized atmosphere, the electrified plasma, the alien chemistry, but the engine itself remains shrouded in its own brilliant exhaust, a tiny jewel hidden in a blinding fog. Humanity's sharpest eye in space, the venerable Hubble Space Telescope, has been brought to bear on this very problem. Astronomers have used its incredible resolving power to try and pierce the veil of the coma and get a direct look at the nucleus. After countless hours of observation and painstaking analysis, the best answer Hubble can give us is a limit, not a measurement. It can only tell us that the solid core of 3I-ATLA measures no more than 5.6 kilometers across. But here's the crucial part. It could be much, much smaller. The data is consistent with a nucleus as small as just 0.3 of a kilometer in diameter. That is an enormous range of uncertainty, spanning 2 full orders of magnitude in mass. It's the difference between a small mountain and a city block. NASA's official summaries maintain this conservative upper limit, the 5.6 kilometer maximum diameter, because it's the most honest answer we have right now. So, how do you even arrive at a number like that when you can't see the object directly? The process is a masterpiece of scientific deduction and sophisticated image processing. Astronomers use a technique called point spread function modeling. In essence, they try to precisely calculate how the bright, fuzzy light of the coma is spread out in the Hubble image, and then they attempt to mathematically subtract that glow. The goal is to see if there's a tiny, unresolved point of light left over at the center of the nucleus. It is the astronomical equivalent of trying to photograph the glowing filament inside a frosted light bulb by first subtracting all the diffuse light of the bulb itself. It is technically possible, but it is a process fraught with systematic uncertainties. A tiny error in modeling the coma's brightness can lead to a huge error in the final result. The fundamental challenge stems from the comet's own extraordinary activity level. As we've seen, 3I Atlas is a hyperactive outlier. Most comets, when they are still as far from the Sun as 3I Atlas is, show only minimal coma development. This makes detecting their nucleus relatively straightforward. It's a bright point against a dark background. But 3I Atlas is already completely enshrouded in that massive, brilliant carbon dioxide envelope. This creates a bright, glowing background that completely overwhelms the much, much fainter light that is simply being reflected by the solid nucleus itself. It's like trying to spot a firefly in the middle of a fireworks display. This uncertainty has led to a fascinating scientific debate. As we mentioned, some of the very early estimates, based on a different technique, suggested a dramatically larger nucleus, perhaps as big as 46 kilometers across. These calculations were trying to work backward. They measured the total brightness of the comet, coma, and nucleus combined, and then tried to calculate how big the nucleus would have to be to produce that much light. But this method is built on a tower of assumptions. You have to assume its albedo, the reflectivity of its surface. You have to assume its dust production rates. And these are assumptions that may simply not hold true for an interstellar object with an alien chemistry and a surface that has been weathered by a billion-year journey through the void. This controversy highlights a fundamental problem in all of comet science. Determining the size of the nucleus is heavily dependent on assumptions about surface properties that we usually can't measure directly. Is the surface dark, like fresh asphalt, reflecting very little sunlight? If so, it would need to be larger to produce the observed brightness. Or is it bright, like fresh snow? In that case, it could be much smaller and still appear just as bright. Without an independent way to know, these size calculations become exercises in highly educated guesswork. Hubble's direct imaging constraint elegantly sidesteps most of these assumptions. By trying to directly detect the nucleus as a point source against the coma's background glow, it gives us a more robust, if less precise, answer. But even Hubble's measurement carries its own significant uncertainties. The modeling process requires a perfect understanding of how the telescope's optics spread starlight, and any small errors in this calibration can propagate into large errors in the final nuclear size limit. Furthermore, there's always the possibility that the nucleus has an extremely dark surface, darker than any typical asteroid or comet nucleus we've ever seen. If that were the case, it might still remain undetected even if it is slightly larger than 5.6 kilometers. And this single, frustrating uncertainty, the size of the engine cascades down into every other aspect of the science of 3IATLAS. Our models of its gas production rates, our understanding of its surface composition, our predictions for its future activity, all of these depend critically on knowing the total surface area of the nucleus that is available for ice sublimation. A tiny 3-kilometer nucleus has roughly 100 times less surface area than a large 30-kilometer nucleus. To achieve the same observed level of gas production, the smaller nucleus would require a dramatically different, almost impossibly efficient sublimation process. This uncertainty reveals something profound about the very nature of cometary activity. We tend to think of comets as simple, dirty snowballs, where bigger objects naturally produce more gas and dust. But 3IATLAS is screaming at us that the relationship between nucleus size and activity level can be far more complex, far more mysterious than we ever imagined. A small but hyperactive nucleus might be a sign of an unusual ice composition, a super-efficient heat transfer mechanism within the nucleus, or a complex surface riddled with fractures and cavities that dramatically maximize the area available for sublimation. Perhaps most frustratingly of all, this size uncertainty directly affects our ability to predict the future behavior of 3I Will its incredible gas production continue to increase as it gets closer to the Sun? Will that already enormous coma grow even larger? Or will depletion effects begin to kick in, causing its activity to level off or even decrease? The answers to these questions depend critically on how much ice remains hidden within the nucleus, and how efficiently that ice can sublimate under the increasing heat of the Sun. Without knowing the size of the fuel tank, it's very difficult to predict how long the engine can run at full throttle. What emerges from all of this uncertainty is a powerful reminder that science often proceeds not through sudden, definitive breakthroughs, but through a gradual, painstaking process of refinement. That 5.6-kilometer upper limit from Hubble represents our best current constraint on the nucleus of 3IATLAC, but it is certainly not the final answer. As the comet gets closer, as its geometry changes relative to us and the Sun, And as new observations from powerful telescopes, like the JWST, accumulate, that range of uncertainty should, hopefully, begin to narrow. The mystery of the nucleus size also highlights the unique scientific value of these interstellar objects. Every single measurement we make of 3I Atlas has to be interpreted without the benefit of decades of previous observations or any detailed knowledge of its formation conditions. We are, in a very real sense, learning comet physics from scratch, using an object whose properties may be fundamentally different from anything in our entire catalog of experience. When 3I Atlas finally completes its spectacular flyby of our solar system and heads back out into the interstellar darkness, it will carry with it whatever secrets its nucleus still holds. Our window of opportunity for resolving this central mystery is incredibly brief, spanning just 18 months from its discovery to its effective departure. The clock is ticking, the telescopes are watching, and somewhere, hidden deep inside that blazing, stellar-sized coma, lies a tiny, solid nucleus whose true dimensions will ultimately determine how we understand this most extraordinary, most mysterious, and most welcome visitor. The story of 3I Atlas is in many ways a story about learning to see the invisible. It is about measuring the seemingly unmeasurable and discovering that a concept as simple as size is a far more slippery, far more profound idea than most of us realize. If I were to ask you, how big is this comet really? The answer would depend entirely and dramatically on a follow-up question. What kind of light are you using to look at it? Because this single object presents two completely different faces to the universe, one visible and familiar, the other vast, ethereal, and completely hidden from our human senses. It is a cosmic Russian doll, with worlds hidden within worlds. Let's start with the face we can comprehend, the one revealed in visible light, the same wavelengths our eyes evolved to detect. In this light, 3I Atlas appears as a classic, fuzzy, star-like object. Powerful ground-based telescopes, like the magnificent Gran Telescopio Canarias, capture this optical coma as a compact, relatively dense cloud of dust and gas, brightly illuminated by reflected sunlight. If you were to measure this visible cloud, you'd find it's roughly 26,400 kilometers across. Now, let's not downplay that. That is an impressive size by any terrestrial standard, about 2 Earth diameters wide. For an active comet at this distance from the Sun, that's fairly typical, impressive, but not record-shattering. This is the comet we would have seen for most of astronomical history. But now, let's perform a kind of cosmic magic trick. Let's switch our vision. Let's look at the very same comet at the very same moment in time, but through the eyes of a near-infrared telescope like Spherix or the JWST. And in this light, 3I Atlas transforms into something utterly, breathtakingly different. The familiar Earth-sized fuzzball vanishes, and in its place, a gossamer, ghostly envelope of carbon dioxide materializes, stretching at least 348,000 kilometers in every single direction. Suddenly, our comet is 696,000 kilometers across roughly half the diameter of our own Sun. It's the same object, yet its apparent size has just increased by a factor of more than 25. This isn't a measurement error. It's not an instrumental bias. It is fundamental physics, and it is a powerful lesson in the nature of reality. Different molecules in the universe interact with light in different ways. They emit, absorb, and reflect light at very specific wavelengths, making them either brilliantly visible or completely transparent, depending on which part of the electromagnetic spectrum you happen to be examining. The optical coma, the one we see with our eyes, is primarily tracing the larger dust particles and certain gas species that interact strongly with visible sunlight. The colossal infrared envelope, on the other hand, is revealing the vast population of carbon dioxide molecules. These molecules glow brightly in the thermal infrared as they are warmed by the sun, but they remain almost completely invisible to our eyes. Think of it like looking at a jellyfish in the ocean. In bright, normal sunlight, you see its dense, gelatinous bell and its trailing tentacles. It's a compact, clearly defined creature, easy to measure. But now, imagine you could switch your vision to ultraviolet. Suddenly, the entire creature might light up with a faint bioluminescence, a ghostly glow that extends far beyond its visible physical boundaries. It's the same organism, but a different kind of light reveals a completely different aspect of its true extent. This is precisely what is happening with 3I TLAs. This nested, multi-layered structure of the comet's atmosphere creates a kind of cosmic Russian doll, each layer revealing a different part of its story. At the absolute center, so small it's effectively invisible, lies that elusive nucleus, no more than 5.6 kilometers across. Wrapped around that is a dense inner coma of dust and mixed gases, the part we see in visible light, extending out to roughly 13,000 kilometers in radius. And beyond that, a much more tenuous but vastly larger envelope of carbon dioxide stretches for hundreds of thousands of kilometers into the vacuum of space. A ghostly giant detectable only in those very specific infrared wavelengths. Each of these layers tells a different part of the comet's ongoing story. The inner optical coma is where the action is most intense. It reveals how dust and gas interact in the immediate vicinity of the nucleus, where sublimation rates are at their highest and particle densities remain substantial. This is the region that undergoes rapid, dramatic evolution as the sun's heating changes, developing the beautiful jets, spirals, and asymmetries that make comet photography so compelling. The outer, carbon dioxide envelope, however, operates on much larger scales and over much longer timescales. The gas molecules in this vast region have been traveling outward from the nucleus for days or even weeks, expanding and cooling as they move through the void. Their incredibly low density makes them invisible to optical telescopes, but their sheer numbers make them a bright beacon in the infrared, where the characteristic vibrations of the carbon dioxide molecule produce bright emission lines. And the JWST's incredible spectroscopic observations have revealed even more complexity, another, even more subtle layer within this infrared envelope. It has detected the signature of water ice grains, each less than 1 micrometer across, scattering short wavelength infrared light. These tiny frozen crystals probably condense directly from water vapor in the cold outer regions of the coma, forming a vast population of particles that are too small to see individually, but which become detectable through their collective light-scattering properties. It's a haze within a fog within a ghost. This complexity, this wavelength-dependent definition of size, creates a real communication challenge for astronomy educators and journalists. Headlines proclaiming that 3I ATLAS is half the sun's width are technically accurate and wonderfully evocative, but they can be misleading if the public assumes this refers to the solid comet itself. The crucial distinction between the tiny nucleus, the medium-sized optical coma, and the colossal extended atmosphere requires careful, patient explanation to avoid confusion and to convey the true, nuanced wonder of the discovery. But this measurement complexity reflects a broader, more profound truth about almost all objects in the universe. They rarely have a single, simple, well-defined size. Think about a galaxy. It appears very different in the visible light of its stars versus the radio waves emitted by its cold gas clouds. A star like our sun has a visible surface, the photosphere, but it also has a chromosphere and a multi-million degree corona that extends for millions of kilometers into space. Planets have solid surfaces, but they also have atmospheres and vast, invisible magnetospheres that define multiple boundaries, depending on what physical process you are trying to measure. 3I ATLAS simply pushes this concept to an almost absurd extreme. The ratio between its tiny nuclear diameter and its colossal carbon dioxide envelope spans a staggering 5 orders of magnitude. That is roughly the same as comparing the size of a single marble to the entire state of Texas. No other object in our solar system demonstrates such a dramatic, breathtaking range of characteristic scales within a single unified system. What emerges from this tale of two sizes is a powerful lesson about the absolute importance of multi-wavelength astronomy. It is a reminder that we cannot hope to understand the universe by looking at it through a single narrow window. Each part of the electromagnetic spectrum, from radio waves to gamma rays, reveals different physical processes, different spatial scales, and different patterns of evolution over time. 31ATLAs isn't uniquely large or uniquely small. It is uniquely complex, with characteristic dimensions that span 5 orders of magnitude depending on what you're measuring, and crucially, how you're measuring it. It is a masterclass in the hidden, multi-layered reality of the cosmos. Orbital mechanics, the silent, gravitational waltz of celestial bodies, can sometimes feel like an abstract mathematical exercise. But in the case of 3IATLA, its precise trajectory through our solar system is anything but abstract. It has a cosmic itinerary that seems almost intentionally designed to maximize both the scientific opportunity and the dramatic potential. This isn't just a random wandering. This is a carefully choreographed, high-speed dance between gravity and velocity that will showcase the physics of an interstellar comet under the most revealing, most intense conditions possible. The numbers of its orbit don't just describe a path. They tell a story of a head-on encounter with the very architecture of our solar system. Let's break down the geometry, because it is the key to everything that is about to unfold. The comet's orbital inclination is 175 degrees. To a non-astronomer, that might sound like just another number, but it is critically important. It means that 3I Atlas is moving in a retrograde direction. It is traveling in almost the exact opposite direction to the motion of all the planets. Imagine a busy, multi-lane roundabout where all the traffic is flowing counterclockwise, and suddenly, a single vehicle enters going clockwise at high speed. That is 3IATLAS, but it gets even more dramatic. Its orbit is also nearly coplanar with the ecliptic. It has tilted only about 5 degrees from the flat plane, where all the planets conduct their stately orbits. This combination retrograde motion, nearly in the same plane, creates the worst possible traffic pattern. It is, in effect, a cosmic head-on collision course, not with any single planet, but with the entire dynamic system of our solar system itself. And because of this unique geometry, the sequence of encounters on its tour reads like a planetary greatest hits list, gone slightly wrong. The first major event is on October 3rd, a close flyby of Mars at just 0.19 astronomical units. That is close enough that the red planet's own gravity will measurably deflect the comet's trajectory, a subtle gravitational nudge that our instruments can detect. Then, on October 29th, comes perihelion, its closest approach to the Sun, placing 3I Atlas in the dynamic region between the orbits of Earth and Mars. Just a few days later, on November 3rd, it will have a distant encounter with Venus. Then, on December 19th, it makes its closest approach to our own planet, a safe but scientifically precious 1.8 astronomical units. And the grand finale? A close flyby of the king of planets, Jupiter, at just 0.36 astronomical units on March 16, 2026. Each of these encounters is far more than just a close pass. They are unique opportunities for gravitational physics, for plasma interaction studies, and for multi-point observations that might only occur once in a century for any given comet. The retrograde geometry means that during each of these planetary encounters, 31ATLAS will be moving at its maximum relative velocity. It will be screening past these planets. This compresses the observation windows, forcing astronomers to be incredibly precise with their timing. But it also maximizes the drama of the gravitational and plasma interactions. It's like studying a test subject in a wind tunnel, But instead of turning up the fan, the subject itself is coming in at supersonic speeds. This nearly ecliptic trajectory also carries profound implications for the comet's interaction with the invisible structures of the solar wind. The ecliptic plane isn't just the flat sheet where the planets orbit. It's also where the sun's most complex magnetic dynamics play out. Remember that vast, wavy boundary, the heliospheric current sheet, where the sun's magnetic field changes polarity. It oscillates up and down, centered on the ecliptic, as the sun rotates every 27 days. Most comets, with their highly inclined or elliptical orbits, spend relatively little time near this magnetic boundary. They cross it quickly and move on. But not 3IATLAS. Its unique path means it will cruise along this magnetic boundary for months on end, repeatedly crossing back and forth between regions of opposite magnetic polarity. Each and every one of these crossings is a potential trigger for a spectacular tail disconnection event, for plasma instabilities, and for the kind of jaw-dropping space weather phenomena that make comet photography so compelling. Ironically, the very geometry that makes this visit so scientifically rich also makes it incredibly difficult to observe from Earth at the most crucial moment. Around the time of perihelion, when the comet's activity should be at its absolute peak, an event called solar conjunction will occur. This is when the comet will pass nearly behind the sun from our perspective. The intense glare of our own star will make ground-based observations completely impossible during this period of maximum activity. It is the perfect example of astronomy as equivalent of Murphy-Sess law. The most interesting events often happen when we are least able to see them. But the same retrograde trajectory that complicates our Earth-based observations creates unique and priceless opportunities elsewhere in the solar system. While we on Earth are blinded by the sun's glare, our robotic emissaries at Mars will have an absolutely perfect view. During the October 3rd flyby, as seen from the red planet, 3I Atlas will blaze at a magnitude of 11. That is bright enough for the cameras and spectrographs on our Mars orbiters to conduct detailed imaging and chemical analysis. This could, potentially, provide our very first spacecraft observations of an active interstellar comet, a truly historic moment in planetary science. The speed implications of this geometry are simply staggering. At perihelion, 3I Atlas will be moving at 68 kilometers per second relative to the Sun. As we said, that's fast enough to cross the continental United States in about 90 seconds. Coordinated observation campaigns must account for this incredible velocity when they plan their telescope pointings and exposure sequences. If you miss your timing window by just a few hours, the comet will have moved significantly against the background stars. It is a fast-moving, fleeting target, and we have only one chance to get it right. And the encounter with Jupiter in March 2026 offers perhaps the most scientifically valuable opportunity of the entire tour. By then, 3I ATLAS will be far from the heat of perihelion and moving through a very different solar wind environment. The space weather in the outer solar system is dominated not by the chaotic CMEs of the inner system, but by high-speed streams and structures called co-rotating interaction regions. These conditions might trigger entirely different types of plasma phenomena, giving us a more complete picture of how the comet behaves in different environments. The orbital geometry even affects the visible beauty of the comet, how its dust and ion tails develop and evolve. Dust tails, composed of larger particles, are pushed gently by the pressure of sunlight, so they tend to point steadily away from the sun. But ion tails, made of electrically charged gas, are sculpted by the magnetic field lines in the solar wind. Because of the comet's retrograde motion, these two tails will sometimes point in dramatically different directions, creating the distinctive, beautiful, forked appearance that makes comets so photogenic. What emerges from this deep dive into the comet's geometry is a profound appreciation for how the silent laws of orbital mechanics can amplify scientific opportunity. The trajectory of 3I Atlas isn't just a path through space. It is a prescription for maximum interaction with every single component of our solar system's complex, dynamic, electromagnetic environment. The very same geometry that makes our observations so challenging is also what makes them so uniquely valuable, providing us with a deluge of data that we might not be able to obtain again for centuries. It is, in every sense, a collision course with discovery. When a messenger from another star system arrives in our cosmic neighborhood, humanity does not sit idly by. We respond with everything we've got. The observational campaign currently targeting 3I-ATLA represents the largest, most complex, most coordinated study of a single comet in the entire history of astronomy. It is a testament to our insatiable curiosity. We have marshaled our most powerful ground-based telescopes, our most sophisticated space observatories, and a global army of citizen scientists into a single, unified effort. The goal is simple, yet profound, to extract every possible piece of information, every photon of light, every chemical secret from this ancient wanderer before it vanishes back into the interstellar darkness forever. This isn't just a series of observations. It is an armada. Leading the charge, like the flagship of this armada, is the James Webb Space Telescope. Its near-infrared spectrograph is the ultimate tool for dissecting the comet's chemical makeup. It's performing a kind of cosmic autopsy from millions of kilometers away, examining the comet's coma across a whole suite of carefully chosen wavelengths that reveal different chemical components. At 1.2 micrometers, the telescope meticulously maps the distribution of dust, studying its scattering properties. At 2.7 micrometers, it hones in on the faint emissions of water vapor, painting a detailed picture of H2O production rates and their spatial distribution within the coma. Then, it turns to the star of the show. At the 4.3 micrometer band, it traces the overwhelming signature of carbon dioxide, the comet's dominant volatile component. And at 4.7 micrometers, it searches for the fainter signatures of carbon monoxide, a key molecule that can help constrain the temperature and irradiation history of the environment where the comet was born. These JWST observations are far more than just pretty pictures. Each wavelength band corresponds to specific molecular vibrations and electronic transitions that encode a treasure trove of information about the temperature, the density, the velocity, and the precise composition of the gas throughout the comet's enormous atmosphere. This spectroscopic data allows astronomers to construct stunning, three-dimensional maps of chemical abundance, essentially performing a dissection of interstellar ice chemistry on a scale that would be impossible to achieve in any laboratory on Earth. Complementing JWST's deep focus dives is the work of the Spherics Observatory. Where JWST acts like a microscope, Spherics acts like a wide-angle lens, capturing the full, magnificent extent of 3I Atlas in near-infrared wavelengths. It was this space-based survey telescope that traced the carbon dioxide envelope out to its current, mind-boggling limit of a 348,000-kilometer radius, revealing that the detectable atmosphere extends far beyond even the most optimistic theoretical predictions. Spherics also identified the subtle absorption signatures of water ice, a crucial finding that indicates that solid particles throughout the coma are continuing to condense and sublimate as they expand outward from the nucleus. And then there is the legend, the Hubble Space Telescope. It brings its unparalleled sharp vision to bear on the most challenging target of all, the comet's innermost regions. Its mission is to resolve the structure of the nucleus itself, or at the very least, to constrain its size through that painstaking process of point spread function modeling. These observations are pushing Hubble's incredible capabilities to their absolute limits, requiring the most sophisticated image processing techniques to separate the faint, almost non-existent signal of the nucleus from the overwhelmingly bright glare of the surrounding coma. The resulting 5.6-kilometer upper limit on the nucleus diameter represents one of the most challenging, most technically demanding small object measurements that Hubble has ever attempted in its multi-decade history. Back on Earth, our magnificent ground-based observatories face their own unique set of challenges. As we know, the comet's trajectory is taking it through the densest star fields visible from Earth. This requires incredibly careful background subtraction and field identification just to isolate the comet as faint light from the sea of stars it's moving through. Giant telescopes like the 8-meter mirror of Gemini North on Mauna Kea provide the immense light-gathering power necessary to conduct detailed spectroscopy even under these crowded and difficult conditions. They are monitoring how the composition and activity levels of 3I-ATLA evolve night after night as the sun's heating effect steadily increases. But this armada is not just composed of giant professional machines. The amateur astronomy community has embraced 3I Atlas with a level of enthusiasm and dedication that is normally reserved only for the brightest, most spectacular periodic comets. Networks of citizen scientists, like the Virtual Telescope Project, are providing crucial cadence observations. They are tracking the small, night-to-night changes in the comet's morphology and brightness, filling in the gaps between the scheduled observations of the large professional observatories. These amateur contributions are proving to be especially valuable for monitoring the kind of rapid, unexpected changes that might occur as the comet interacts with the solar wind, changes that might be missed by a professional telescope that only looks at the comet once a week. Coordinating all these different assets requires a level of precision that is unprecedented. Because 3I Atlas is moving so fast, the timing of observations must be synchronized to within hours to ensure that different telescopes are actually studying the same physical phenomena. A system of target of opportunity scheduling allows major observatories to react quickly, to pivot their schedules to respond to any unexpected changes in the comet's behavior, like a sudden outburst of gas or a tail disconnection event. But coordinating these rapid responses across multiple time zones, multiple institutions, and multiple continents presents logistical challenges that are testing the very limits of modern astronomical collaboration. This multi-wavelength, multi-observatory approach is essential because each technique reveals a different piece of the puzzle. Future ultraviolet observations planned for Hubble will probe the atomic emissions from the very innermost coma, where gas densities remain high enough for a process called collision-induced fluorescence to occur. Optical wavelengths trace the scattering of sunlight off dust particles. The near-infrared reveals the thermal glow from warm dust and the vibrational fingerprints of the major gas species. And radio observations from telescopes like Alamy might just be able to detect the faint signatures of exotic trace molecules that could provide even deeper clues about the comet's origin. The observational armada's scope even extends beyond traditional astronomical facilities. As we've hoped, the flotilla of spacecraft currently orbiting Mars, including the European Space Agency's Mars Express and NASA's MAVEN, might attempt to make observations during the October 3rd flyby. This could provide our first ever direct, in situ measurements of an interstellar comet's plasma environment, complementing the remote sensing data from Earth with direct particle and field measurements that would be impossible to obtain from our distant vantage point. What emerges from this coordinated observational campaign is a new model for how we study rare, transient astronomical phenomena. Rather than relying on the serendipitous observations of individual research groups, the arrival of 3I Atlas has prompted the entire astronomical community to develop a systematic, collaborative approach that is designed to maximize the scientific return from these fleeting, priceless opportunities. This template, this global battle plan, will prove invaluable when future interstellar objects arrive, ensuring that humanity is ready to extract the maximum possible scientific value from each and every cosmic visitor. The armada targeting 3I-ATLAS represents more than just telescope time and data collection. It is a powerful, inspiring demonstration of how modern science operates as a global enterprise, combining cutting-edge technology with international cooperation and passionate citizen participation to answer the most fundamental questions about our place in the galaxy. Solar maximum has arrived. The sun, our seemingly placid and life-giving star, is waking up. And 3I Atlas could not have picked a more dramatic, more opportune, or more dangerous time to visit. Our sun is approaching the peak of its activity in its natural 11-year magnetic cycle. It's a period of solar tempests, a time when it spawns colossal coronal mass ejections, unleashes ferocious high-speed wind streams, and creates the kind of chaotic, twisted magnetic field conditions that can transform a comet's gentle, ethereal tail into a spectacular, violent display of celestial violence. This is the stage upon which our interstellar visitor will perform. But before we dive into the fireworks, let's be absolutely crystal clear about cause and effect here. 31ATLAS did not trigger solar maximum, and solar maximum is not, in any way, responding to the presence of 3I-ATLAS. The sun operates on its own grand, magnetic schedule, completely indifferent to whatever tiny visitors happen to be passing through the inner solar system. What we are witnessing is a case of pure, unadulterated, and for science, incredibly fortunate, cosmic coincidence. An ancient wanderer from the dawn of the galaxy has arrived at our doorstep, just as our star is entering its most temperamental and violent phase. And this timing creates an unprecedented, once-in-a-lifetime opportunity to study the intricate physics of a comet's plasma under the most extreme conditions imaginable. Let's talk about the main event: coronal mass ejections, or CMEs. These are the apex predators of the solar system. These are billion-ton blobs of magnetized plasma, gargantuan magnetic bubbles, hurled from the sun's surface at speeds that can reach up to 2,000 kilometers per second. During solar maximum, these events can occur several times a week. When one of these magnetic monsters, traveling with unimaginable force, slams into the extended, half-sun-sized atmosphere of 3I-ATLAS, the results should be nothing short of spectacular. We can expect to see its vast coma get visibly compressed by the shock wave. We will likely see its tails completely restructured in a matter of hours. And we may even witness a complete tail disconnection event, a moment where the magnetic field lines of the CME snap and reconnect with the comet's own plasma field, with explosive force appearing to tear the tail clean off. We have seen historical precedents for these kinds of violent space weather interactions. Back in 2007, the magnificent comet McNaught experienced a series of dramatic tail disconnections during a period of only moderate solar activity. The images that were captured looked more like cosmic lightning bolts, jagged and torn, than the gentle, curving streamers we typically associate with comet tails. Now, just imagine what we might see with 3I-ATLAS, with its absolutely massive atmosphere acting as a giant target, and its arrival during the peak of solar maximum. It could produce displays of celestial plasma physics that are even more dramatic, even more awe-inspiring. The physics that underlies these incredible interactions reads like a graduate-level textbook on plasma instabilities, but the core concept is one of explosive energy release. When the magnetic field of an incoming CME encounters the ionized coma of 3I Atlas, the two separate magnetic environments don't just merge smoothly. Instead, they can undergo a process called magnetic reconnection. This is a violent event where opposing magnetic field lines break and then reform into a new, more stable configuration. In the process, an enormous amount of stored magnetic energy is released in a fraction of a second. This released energy can heat the plasma in the comet's coma to millions of degrees and accelerate ions to velocities approaching 1% of the speed of light. It is a natural, cosmic explosion. And once again, the unique orbital geometry of 3I Atlas seems tailor-made to amplify these space weather effects. The comet's nearly ecliptic trajectory means it will spend months cruising along the heliospheric current sheet, that vast, wavy boundary where the sun's magnetic field reverses polarity. As we've seen, most comets cross this boundary quickly. But 3I Atlas will repeatedly surf this magnetic wave, encountering regions of opposite magnetic polarity again and again, creating multiple sustained opportunities for these dramatic plasma interactions to occur. It's like sending a ship not just through a single storm, but through an entire prolonged hurricane season. The European Space Agency's Rosetta mission gave us our first truly intimate, up-close view of how solar storms can affect a comet's environment. And even the relatively quiet, well-behaved Comet 67P showed a remarkable sensitivity to even minor variations in the solar wind. Its plasma densities and magnetic fields fluctuated dramatically in response to relatively gentle changes in solar activity. Now, just scale that up. 31ATLAS has activity levels that are orders of magnitude higher than Comet 67P. It should, therefore, amplify these effects proportionally, acting as a much more sensitive and spectacular barometer of solar activity. The visual signatures of these space weather interactions will appear across multiple wavelengths and on different timescales, giving our observing armada a rich variety of phenomena to study. Ultraviolet emissions should spike dramatically when magnetic reconnection heats the plasma in the inner coma. Our optical images will reveal the dramatic kinks, rays, and disconnection events in the dust and ion tails as they respond differently to the magnetic forces versus the gentle pressure of sunlight. And radio emissions might even spike as the accelerated particles generate plasma waves that propagate throughout the comet's extended atmosphere. The distinction between the dust and the ion tails will become crucially important during these space weather events. Dust particles are electrically neutral and relatively large. They respond primarily to the simple pressure of photons from sunlight, which means their tail will continue to point steadily away from the sun, regardless of what the magnetic field is doing. But the ion tail, composed of electrically charged gas molecules, is a completely different story. It is a slave to the magnetic field. It will couple directly to the magnetic field lines of the solar wind and can be seen to swing about dramatically like a flag in a gale as the magnetic fields change their orientation during the passage of a CME. Predictions for specific space weather events remain, by necessity, a bit vague. This is because solar activity follows chaotic, rather than neatly predictable, patterns. We can estimate the statistical probabilities. For example, there is perhaps a 50% chance of at least one major coronal mass ejection directly hitting the comet during its passage through the inner solar system. But predicting the precise timing of these events is currently beyond the capabilities of our space weather forecasting. This is why the continuous monitoring by the amateur astronomy community is so vital. They can act as a global real-time alert system, reporting any sudden changes in the comet's tail morphology or brightness, providing the crucial real-time data that the large professional observatories, with their rigid schedules, might otherwise miss. What we must avoid in all this excitement is ascribing any kind of agency or intent to these natural processes. 31 Atlas does not cause solar storms any more than a weather vane causes the wind. The comet is simply serving as an exquisitely sensitive, perfectly placed probe of space weather conditions. It is a scientific instrument disguised as a visitor from another star. It is revealing the intricate, invisible structures of the solar wind and the variations in the sun as magnetic field that would otherwise remain completely hidden from our view. The space weather forecast for the solar system passage of 3I Atlas reads like a cosmic weather report for a perfect storm. A high probability of magnetic turbulence, excellent chances for spectacular tail disconnection events, and priceless opportunities to study the fundamental principles of plasma physics under the most extreme natural conditions that our local stellar environment can possibly provide. The show is about to begin. The incredible scientific return from studying 3I Atlas extends far beyond just characterizing one weird comet. This is not just a single data point. This ancient wanderer is a messenger, carrying fundamental information that has the potential to reshape our understanding of planet formation, of stellar evolution, and of the sheer chemical diversity of planetary systems all across our galaxy. Every single spectrum, every image, every precise measurement we make is another piece being added to a grand puzzle, a puzzle that spans billions of years in time and thousands of light years in distance. The scientific payoffs are operating on a truly terrifying and exhilarating scale. The most immediate and revolutionary scientific payoff is in the field of interstellar chemistry benchmarking. That extreme 8-to-1 carbon dioxide to water ratio does more than just raise eyebrows. It completely demolishes a long-held assumption and establishes a new extreme endpoint for the diversity of comet composition. For decades, our observations, limited to comets from our own solar system, suggested that a water-dominated chemistry was a universal, or at least very common, feature of comet-forming environments. 31ATLAS proves that assumption to be catastrophically wrong. A 6 sigma deviation from the norm isn't just an unusual finding, it's a revolutionary one. It is forcing scientists to completely revise their models for how ices can condense and accumulate in the protoplanetary disks that form around young stars. And the implications of this single finding cascade down through all of planetary science. Just think about it. If the composition of 3I-ATLA, as is typical for comets that form in the cold outer regions of a star system, then it means that planetary systems around different types of stars might have radically different inventories of volatile materials than our own water-rich solar system. Consider M-dwarf stars, the small, cool, red stars that are the most common type in our galaxy, making up about 75% of the stellar population. These stars create very different temperature and irradiation environments during the critical phase of planet formation. Is it possible that 3I Atlas is our very first direct sample of the chemistry of an M-dwarf system? It's a tantalizing possibility. The study of dusty plasma physics is also receiving an unprecedented gift. The enormous, active coma of 3I-ATLAS is serving as a natural laboratory, an experiment on a scale that is simply impossible to reproduce artificially. The complex magnetic field interactions, the subtle dust charging processes, the powerful ion acceleration mechanisms, all the phenomena we study around 3I-ATLAS will directly inform plasma physics research in a wide range of other fields, from the design of future fusion reactors here on Earth to the modeling of the vast, tenuous interstellar medium between the stars. The Rosetta mission provided our first incredibly detailed, up-close measurements of these plasma phenomena around a relatively quiet comet. But 3I-ATLAS offers us the chance to study these same processes at extreme, almost unbelievable, activity levels. The ion densities, the magnetic field strengths, and the plasma wave amplitudes in its coma should exceed anything measured at Comet 67P by orders of magnitude, pushing our plasma physics models into completely unexplored territory. We are also gaining powerful new constraints on planetary formation. The unique chemical fingerprint of 3I-ATLAS will help scientists calibrate their models of how protoplanetary disks evolve around different types of stars. As we've seen, its carbon dioxide dominance suggests one of two main scenarios. Either it formed at a very large distance from its host star, in a region where CO2 ice could condense directly, or it was exposed to incredibly intense stellar irradiation that preferentially stripped away its water. Each of these scenarios implies very different conditions in its birth stellar system. Formation at large distances would require protoplanetary disks to be more massive and more extended than our typical solar system models predict. Irradiation processing, on the other hand, demands proximity to very luminous massive stars that could provide the necessary flood of ultraviolet flux. Both of these possibilities significantly expand the range of environments where comet formation might occur. which in turn increases our estimates for the total population of interstellar objects throughout the galaxy. And this brings us to the grandest scale of all, galactic archaeology. The likely origin of 3I Atlas in the galaxy's ancient thick disk is an enormous scientific boon. Objects with ages that can exceed 7 billion years are physical samples of the stellar formation, conditions from a time when our galaxy was younger, more chaotic, and chemically distinct from the present epoch. The comet's composition preserves the isotopic ratios, the elemental abundances, and the ice chemistries from this ancient environment, providing direct physical constraints on our models of how the galaxy itself has chemically evolved over billions of years. The thick disk population formed during an era when stellar metallicity, the abundance of elements heavier than hydrogen and helium, was significantly lower than it is today. If 3I Atlas truly is a representative of this ancient population, its chemical composition should reflect these lower abundances, providing a crucial check on our theories of nucleosynthesis and early galactic evolution. Finally, the statistics of the interstellar object population are receiving crucial calibration data from every single confirmed detection. 31ATLAS, combined with Oumuamua and Borisov, establishes the beginning of a true statistical sample. This sample helps us constrain our models for how often stellar systems eject their small bodies into interstellar space. Current estimates suggest that every single star system loses thousands, or perhaps even millions, of small bodies during its turbulent evolution, creating a galaxy-wide, unseen population of wandering objects that could number in the quintillions. The incredible chemical diversity we've already observed across just these 3 interstellar objects, from Oumuamua's apparent rock-like nature to Borisov's carbon monoxide enhancement to the extreme carbon dioxide dominance of 3I Atlas, strongly suggests that there is an enormous variety in formation conditions across different stellar systems. This diversity challenges our simple, sun-centric models of planetary system architecture. It implies that habitable worlds, and the comets that might deliver water and organic materials to them, could form under a much broader, much more exotic range of conditions than we had ever previously thought. We are expanding the very definition of a planetary system. We are moving from a science of comparative planetology, comparing planets and moons within our single stellar system, to a truly galactic scale. We can now begin to compare the formation products from completely different stellar environments. 31ATLAS may represent the chemical data from an M-dwarf system, or a binary star environment, or a violent stellar nursery with properties completely unlike the relatively gentle environment where our own sun was born. We're not just studying a comet. We are conducting a comprehensive survey of the conditions in an alien stellar system, a system whose chemistry was preserved in ice and then delivered directly to our doorstep after a billion-year journey through the cold, dark silence of space. The Interstellar Object Hall of Fame is an exclusive club. At present, it consists of exactly 3 members. And if you had set out to design 3 objects to showcase the full, bewildering range of cosmic possibilities, you couldn't have done a better job. Each of our 3 confirmed visitors represents a completely different class of object, a different formation environment, and a different evolutionary pathway. Collectively, they are beginning to paint a picture of the galactic debris field that is so incredibly diverse, so wonderfully strange, that it challenges every single one of our assumptions about what a typical planetary system looks like. They are the first 3 ambassadors from the Galactic Commonwealth of Star Systems. First, in 2017, came 1I Oumuamua. Its arrival was the astronomical equivalent of a cryptic first contact, an encounter that left everyone more confused than enlightened. This bizarre cigar-shaped wanderer showed no detectable coma, no measurable gas production, and no obvious comet-like behavior whatsoever, despite the fact that it was following a clearly hyperbolic interstellar trajectory. Its extreme elongation, its unusual non-gravitational acceleration away from the Sun, and its strange tumbling rotation created a scientific mystery that, even today, nearly 8 years later, remains profoundly unsolved. The theories about its nature proliferated like academic mushrooms after a rainstorm. Was Oumuamua a fragment of a tidally disrupted planet, torn apart by its parent star? Was it a shard of some exotic ice, like solid hydrogen or nitrogen, that sublimated invisibly, eluding our infrared telescopes? Some respected researchers, pointing to its strange acceleration, even suggested that it might represent our very first encounter with a piece of extraterrestrial technology, hypothesis that generated tremendous public interest but found very little support in the sparse observational data. The Oumuamua controversy highlighted both the raw excitement and the inherent dangers of studying these interstellar objects. With incredibly limited observation windows and completely unprecedented phenomena, the line between legitimate scientific speculation and outright sensationalism can become uncomfortably thin. Then, just 2 years later in 2019, came 2I Borisov, arriving like a cosmic palate cleanser after the confusion of Oumuamua. Here, at last, was an object that behaved exactly as astronomers had always expected an interstellar comet should behave. It displayed obvious coma development, it had predictable gas production, and its spectroscopic signatures screamed, "Dirty snowball from deep space." Borisov, in many ways, restored our confidence in the fundamental principles of comet physics. It demonstrated that interstellar objects could, in fact, be studied using our conventional techniques, and that they weren't all baffling enigmas. But Borisov still carried its own subtle chemical surprises. While it was much more normal than Oumuamua, spectroscopic observations revealed that it had unusually high abundances of carbon monoxide. It wasn't nearly as extreme as the carbon dioxide dominance of 3I Atlas, but it was still a significant enhancement compared to the typical comets from our own solar system. This carbon monoxide-rich composition suggested that Borisov had likely formed in a colder environment than most of our local objects experienced, hinting at different thermal conditions in its birth stellar system. Borisov was a clue that the chemistry of other star systems might be subtly, but importantly, different from our own. It represented interstellar chemistry that was unusual, but not revolutionary. And now, 3I ATLAS arrives to complete this bizarre and fascinating trilogy. It brings with it a chemistry so extreme, so far off the charts, that it makes even the unusual Borisov look conventional by comparison. That 8:1 carbon dioxide to water ratio pushes comet composition into completely uncharted territory. A chemical landscape that challenges our most basic assumptions about how ices can condense and accrete in protoplanetary disks. So, if Oumuamua was the mysteriously inactive and stealthy visitor, and Borisov was the reassuringly normal, but still interesting one, then 3I Atlas is the hyperactive, spectacular, and completely unexpected one. And speaking of the JWST, its post-perihelion observation campaign promises to deliver the most detailed chemical analysis of any comet in history. As 3I ATLAS emerges from the sun's glare in November, the mighty space telescope will repeat the same spectroscopic measurements it made on the inbound journey. By comparing the before and after data, astronomers will be able to monitor exactly how the gas production rates and the compositional ratios change in response to the period of maximum solar heating. This comparison is the key. It will finally reveal whether the extreme carbon dioxide dominance represents the intrinsic, fundamental chemistry of the nucleus itself, or if it results from preferential release due to surface effects, like that insulating crust we hypothesized. December 19th will bring the comet's closest approach to our own planet, Earth, at a safe and comfortable distance of 1.8 astronomical units. By then, 3I Atlas will have survived its trial by fire at perihelion and will have begun its long, outbound journey back into the darkness. This will allow astronomers to study how the coma contracts and evolves as the solar heating effect begins to decrease. The timing of this Earth encounter coincides with excellent observing geometry for telescopes in the Northern Hemisphere, which could finally enable the wider amateur astronomy community to contribute meaningful observations. Citizen science networks are already preparing detailed finder charts and observation protocols, hoping to engage thousands of observers worldwide in monitoring the comet's post-perihelion behavior. And then, on March 16th, 2026, comes the grand finale, the Jupiter encounter. The comet will fly by the gas giant at a distance of just 0.36 astronomical units. By then, 3I-ATLAS will be operating under very different conditions than it experienced in the inner solar system. The space weather out by Jupiter is dominated by high-speed wind streams and vast, rotating structures, rather than the chaotic CMEs that characterize the inner heliosphere. Furthermore, Jupiter's own enormous, powerful magnetosphere will add another layer of complexity to the encounter. If 3I Atlas passes through the Jovian magnetic field, its plasma tail could undergo a dramatic restructuring as it transitions from being controlled by the solar wind to being influenced by the planet's magnetic field. These interactions might even be observable from Earth as sudden, dramatic changes in the tail's morphology or orientation. The data from this 18-month performance will continue to yield discoveries for years, even decades, to come. The release schedules from major observatories like JWST and Hubble mean that the scientific results will keep emerging long after 31ATLAS has departed our solar system. The raw data from JWST, for example, typically requires months of intensive processing and analysis before it reaches a peer-reviewed publication. And Hubble's complex UV spectroscopy involves intricate calibration procedures that can extend the analysis timelines by a year or more. We will be learning from this comet long after it is gone. Throughout this entire period, the Minor Planet Center will continue to issue updated orbital elements as new observations refine the comet's trajectory. These updates are absolutely crucial for planning all future observations, ensuring that telescope pointing remains accurate as the comet's high velocity carries it rapidly across our sky. And public engagement activities will track 3I-ATLAS throughout its passage with astronomy education organizations, planning special events around each major encounter, using the comet's interstellar origin and its extreme properties as a natural hook to discuss topics ranging from stellar evolution to plasma physics. The 18-month observation campaign represents humanity's most comprehensive, most ambitious study of any single comet, interstellar or otherwise. It is a marathon, not a sprint. And by the time 3I-ATLAS finally accelerates back into the void in late 2026, we will have accumulated a more detailed, more complete set of measurements of an individual comet than any previous mission or observation campaign has ever achieved. This ancient visitor's brief appearance will continue to yield scientific discoveries for a generation. As 3I Atlas rounds the Sun and begins to accelerate towards its final, irrevocable departure from our solar system, it will carry with it the accumulated weight of 18 months of intense human curiosity, dedication, and wonder. We will be left here, under our familiar skies, to contemplate what terrifying scale really means in an age when the universe seems to reveal new, beautiful impossibilities with each passing year. The legacy of this visitor isn't just in the data it leaves behind. It's in the fundamental shift in perspective forces upon us. First, there is the sheer physical scale. That gossamer, ethereal atmosphere stretching 696,000 kilometers across the void, wrapping a volume half the diameter of the Sun around a nucleus that is smaller than most asteroids. The ratio is so extreme, it fundamentally defies our earthly intuition. It's like discovering that a single marble can generate a fog bank the size of Texas. It's like learning that a single grain of sand can cast a shadow across an entire continent. 3-1 Atlas forces us to completely recalibrate our understanding of how small, seemingly insignificant objects can influence vast regions of space through nothing more than the simple physics of ice sublimation and solar heating. The physics itself scales up in ways that challenge our ability to model or even predict, pushing our most powerful plasma simulations into parameter regimes that no laboratory on Earth could ever hope to reproduce. Then there is the dynamical scale, that incredible velocity of 68 kilometers per second at perihelion fast enough to cross the continental United States in less than 2 minutes. This isn't the leisurely, predictable orbital mechanics of planets. This is the desperate, urgent motion of an object that has already escaped the sun's gravitational embrace, an object that seeks only to minimize its time in what is, to it, alien territory. At such speeds, 3I Atlas experienced our entire, magnificent solar system as nothing more than a brief, fleeting interruption in its billion-year journey through the interstellar void. The 18 months from its discovery to its departure, a significant span of time for us, represent perhaps 1/10,000,000th of its total travel time since it was violently ejected from whatever distant, unknown stellar system gave it birth. We are witnessing the cosmic equivalent of a highway rest stop, a momentary pause in an odyssey that spans geological, almost galactic, time. And this brings us to the temporal scale, which is perhaps the most unsettling, most humbling perspective of all. The kinematic analyses that place 3I at TLA S in our galaxy, S ancient thick disk population, imply an age that could exceed 7 billion years. This silent wanderer may have already been a fully formed object when our own solar system was nothing more than a diffuse nebular cloud. It carries the chemical fingerprints from an epoch when star formation followed different rules, when the heavy elements that make up our world and our bodies were far less abundant than they are today. It has silently witnessed our galaxy's evolution through cosmic epochs we can barely imagine. It survived whatever ancient catastrophe ejected it from its birth system. It cruised through the void while our sun condensed, while the planets formed, while life arose on this small blue world and evolved through billions of years of painful, beautiful innovation. The velocity comparisons alone reveal the dynamic diversity of interstellar space. Oumuamua approached our solar system at a respectable 26 kilometers per second relative to the sun, fast enough to confirm its interstellar origin, but not extraordinarily so. Borisov was a bit faster, moving at about 32 kilometers per second. But 3I Atlas simply screams through our solar system. Its velocity of 58 kilometers per second when it's far from the sun makes it, by a significant margin, the fastest confirmed interstellar visitor we have ever recorded. The orbital geometries of the three objects also paint three completely different pictures of galactic dynamics. Oumuamua followed a steep, highly inclined trajectory that carried it well above and below the flat plane of the ecliptic, minimizing its interaction time with the planets and the most intense regions of the solar wind. Borisov's orbit was more moderately inclined, providing reasonable observation opportunities without the kind of extreme space weather exposure that 3I Atlas will experience. But the near-ecliptic retrograde path of 3I Atlas represents the most dynamically interesting case possible. It ensures the maximum possible interaction time with solar wind structures. It provides multiple planetary encounters, and it carries the highest probability for the kind of dramatic space weather events that we are all anticipating. The public narrative and the scientific communication surrounding these three discoveries has also evolved, revealing how the astronomical community has adapted to the fast-paced, sometimes chaotic, environment of the Internet age. Oumuamua sparked wild speculation about alien artifacts, partly because scientists were being appropriately and correctly cautious about making definitive statements based on very limited and puzzling data. The media, and especially social media, filled that uncertainty vacuum with increasingly exotic and often unfounded explanations. With Borisov, the scientific community benefited from the lessons learned during the Oumuamua episode. Scientists communicated more proactively about what the observations were revealing, emphasizing the comet's largely conventional behavior while still highlighting its genuinely interesting and unusual chemical properties. The result was a much more balanced and accurate public conversation, one that maintained public interest without encouraging baseless speculation. 31ATLAS now represents the newest and most complex test case for science communication in the social media era. Its extreme properties, the half-sun-wide atmosphere, the ancient origin, the unprecedented chemistry provide natural, irresistible hooks for public engagement. But they also require careful, nuanced explanation to distinguish the genuinely unusual and groundbreaking science from the realm of science fiction. What ultimately emerges from comparing our 3 confirmed interstellar visitors is a powerful lesson about the dangers of making generalizations from extremely limited data. Any single object might just represent an extreme outlier with little broader significance. But having 3 objects that show such profoundly diverse properties strongly suggests that the population of objects in interstellar space is incredibly varied, containing representatives of every possible formation environment and every possible evolutionary pathway. The galaxy, it seems, contains small body populations that are far more diverse, far more strange, and far more wonderful than the limited sample within our single stellar system ever suggested. Each new visitor confounds our expectations in a different way, which strongly suggests that our 4th, 5th, and 6th interstellar discoveries will probably surprise us just as thoroughly. We are just beginning to read the first few pages of a vast, galactic library. The next 18 months are going to be a whirlwind. The time from now until the final departure of 3I ATLA S in late 2026 will unfold like a meticulously choreographed cosmic ballet. Our interstellar visitor will pirouette through the inner solar system, and all the while, humanity's most sophisticated instruments will be its audience, documenting every twist, every leap, every breathtaking moment of this ancient wanderer's brief one-time performance on our local stage. The timeline of events reads like a greatest hits album of astronomical opportunities, with each encounter, each milestone, offering unique scientific prospects that may not be repeated for centuries. This is the roadmap for discovery. The opening act is scheduled for October 3rd, 2025. This is the Mars Flyby, a close approach at a distance of just 0.19 astronomical units, or roughly 19 million kilometers. From the perspective of our robotic orbiters at the Red Planet, 31ATLAS will blaze at a respectable magnitude 11. That is more than bright enough for detailed imaging and spectroscopy. If the mission controllers for spacecraft, like the European Space Agency, Mars Express, and NASA Maven, can be convinced to tear their eyes away from their primary geology surveys and look up. These spacecraft carry instruments that are potentially capable of tasting the comet's plasma environment, offering our very first chance at direct, in situ measurements of an interstellar visitor's interaction with a planet's space weather environment. This Mars encounter also creates a fantastic opportunity for triangulation observations. By having our Earth-based telescopes and the Mars orbiters view 3I Atlas simultaneously from 2 very different angles, we can use the principles of parallax to get a better handle on its distance and structure, providing independent constraints that could help us finally resolve the persistent, frustrating uncertainty about the true size of its nucleus. Then, as the performance reaches its climax, a moment of cosmic frustration looms. On October 29th, the comet will reach perihelion, its closest approach to the Sun, at a distance of 1.36 astronomical units. This is the moment when its gas production should reach its absolute maximum intensity, when its coma should expand to its largest and most magnificent extent. But as we've noted, the geometry conspires against us. From our perspective here on Earth, the comet will be in solar conjunction, positioned almost directly behind the Sun. The intense glare will make it completely invisible to our ground-based telescopes during this most scientifically interesting period. But our eyes in space do not suffer from the Sun's glare in the same way. The Hubble Space Telescope has a series of crucial ultraviolet observations planned for this period. These observations are designed to probe the atomic emissions from the very innermost coma, where a process called collision-induced fluorescence can reveal vital information about gas, densities and temperature distributions that are impossible to obtain at any other wavelength. These UV measurements will perfectly complement the earlier infrared spectroscopy from JWST, helping us to build a complete, comprehensive picture of the comet's atmospheric structure across the full electromagnetic spectrum. Yet, for all its ancient heritage, for all its silent patience, 31ATLAS demonstrates the raw electromagnetic vitality that characterizes our modern universe. That half-sun-wide atmosphere isn't just a passive, expanding gas. It is a living, breathing plasma environment where magnetic fields twist and snap, where particles are accelerated to incredible velocities, and where the gentle, persistent pressure of starlight sculpts matter across distances measured in astronomical units. It is both ancient and fiercely alive. But perhaps the most terrifying scale of all is the one that 31ATLAS illuminates within ourselves, the scale of our own ignorance. This single tiny object has revealed profound gaps in our understanding of comet chemistry, of plasma physics, and of galactic evolution gaps that will require decades of future research to fully address. It demonstrates, with brutal clarity, how much we still don't know about the vast universe that lies beyond our immediate stellar neighborhood. 31 Atlas forces us to confront the humbling possibility that our solar system, for all its complexity and beauty, represents just one, perhaps even unusual, example of planetary system architecture in a galaxy that contains billions upon billions of alternatives. The extreme chemistry, the unusual dynamics, and the ancient heritage of this single visitor powerfully suggest that the cosmos harbors phenomena far stranger, far more diverse than our provincial, sun-centric experience has ever prepared us to recognize. When 3I-ATLA finally disappears back into the void in late 2026, it will vanish from our telescopes, but not from our minds. It will carry with it our measurements, our curiosity, and a newfound, profound sense of humility in the face of cosmic scales that will always exceed human comprehension. A terrifying scale, in the end, isn't just about size or speed or age. It is about the profound, soul-stirring revelation that the universe is constantly operating at extremes that challenge our most basic, most cherished assumptions about what is possible. In the final analysis, 3I-ATLAS serves as a powerful, necessary reminder. A reminder that we inhabit a cosmos where ancient wanderers can carry messages across billions of years and billions of kilometers. A universe where tiny, almost invisible objects can generate phenomena on stellar scales. A universe where the vast, dark space between the stars isn't an empty void, but a vast, churning ocean of possibilities that we have barely even begun to explore. The comet's brief, spectacular visit leaves us with questions that will outlive everyone who is currently studying it, ensuring that its legacy will extend far beyond its physical departure. Sometimes the most profound discoveries come not from finding what we expected to find, but from encountering a phenomenon so extreme, so beautiful, so utterly baffling, that it forces us to expand our very definition of what the universe allows. And in that glorious, terrifying expansion of possibility lies both terror and wonder. The recognition that we live in a cosmos far stranger, more violent, and more magnificent than our earthbound experience could ever have suggested. The universe is filled with wonders just like 3I-ATLAS, and our journey to explore them has only just begun. Make sure you resubscribed so you don't miss the next chapter of our voyage into the great unknown. And let us know in the comments what part of this story amazed you the most. Thanks for joining us.